accepted, and if the new error is higher than the old error, then the parameters will be accepted with the probability which is given by um, Boltzmann factor. So here in the Boltzmann factor, here we have a parameter called beta, and we call it beta or inverse of temperature. So whenever I say beta, or you should have you should think about as a temperature. So what it means is that the temperature is higher, the temperature is really high, then this Metropolis Monte Carlo method, it accepts all the moves, and if the temperature is lower, then it accepts only the ones which are lower than the current error. So which means that it goes down in the error surface. So that's the idea. So if we start with for instance, a typical simulated annealing method is when we start with a very high temperature, which means that a lower beta value, and we slowly cool the system down, and we presume that the system goes down to the global minima. That's the essence of the simulated annealing procedure. Now, one of the main advantages of this MMC method over other optimization algorithm is that because of its randomness, it jumps over local maximas easily. So that's one of the main advantage, and that's what we are going to exploit in this ReaxFF force field parameterization, and which in fact is also a challenge in ReaxFF force field optimization. Now, yeah, this is a typical simulated annealing run, which you can see that the error is decreasing as a function of increasing beta, so which means that temperature is going down. Now, today what I'm going to show you is that after this presentation, I will show you how to set up input files, which means that the geo file and the trainset.n file. And then I do a force field optimization at low temperature. Then I will just show you the settings for simulated annealing, but I won't do a simulated annealing because it takes a long time. But I can easily do this optimization at low temperature. That can be done. So I'll show you this low temperature optimization. Now, having said that, I'll go back to my files where I have my DFT data. So nice, this one. So as I said, we need to have the DFT data available for the force field to start with, actually. So what I have here is that I'll just I'll make a minimal training set. So what I mean by here is that I take a couple of magnesium sulfate molecules, and I generate the geo file and the corresponding training set files, just to show you how it can be done. Again, it's just a basic training set, and I'm not going to do optimization based on this file, but I'll be doing optimization with using a different file, but just to show you how this can be set up. So I go to my terminal. No, I go here, and then I open ReaxFF, ADF. So this is working. Yeah. So what I have here is that a set of yeah, ADF is coming. Set of XYZ files. No. Okay. Let me go back to this one. Yeah, so what I have here is a set of data which are in XYZ format. So here is the XYZ format. So yeah, so these are the three separate geometries in XYZ format. So what I'm going to do is I'm going to convert them into BGA format, and that's what we need. That is being identified by, that is the format which is being identified by ReaxFF. So I'm going to convert this into um, um, oh yeah. So what I have is I've converted this into um, BGF format. So GSF minus O minus DZ Geo. Okay. So so here I have a non-periodic geometry. So just a molecule, ADF molecule, which you want to see probably, but maybe that's not necessary. So what I have here is that MgSO4 molecule. So I should give a name for this particular molecule. So this is a name that I give segmentation fault. Oh, okay, sorry. Yeah, so 0 and then yes, and then MgSO4. It couldn't read the file, so it's not a periodic geometry, so that's the reason. So yeah, so now what I have here is that this is a geometry that I have. So open it here. Yeah. So this is a typical gaseous molecule. So we have this one. So uh, yeah. So the coordinates has been transferred already, but now we need the energy of this molecule, so which we can get directly from the ADF log file, which is this energy. So I give this energy as minus 560.75. So I enter this number. Yes. Yeah, so this is being recorded in the geo file. So I can repeat this procedure um, uh, uh, depending on the number of geometries that I have. So what I get here is a format which is readable by ReaxFF, which is identified by ReaxFF. I can repeat this procedure, and I get this geo file. And then for every new geometry, you have to append this new geometry to this file, and you get this geo file. And once you get this geo file, what you need to generate is you need to generate something called the train set.in file, which is shown here. It's not here. Yeah, so it's here. So in the training set file, there are different sections. So what we have in the first section is the charge parameters, and then we have geometry, which actually contains the bond information, and then we have the cell parameters, and then energy parameters, and so on. Now, actually, it's very easy to extract all this information like bond and energy, but if you I just had a talk with Alexei, and then he promised that he will make a tool for you in ADF so that you can easily convert this XYZ or ADF output directly into this training set kind of format. And if you also want, you can also contact me personally. I have these codes which I can easily convert this directly into this format, especially the bond lengths and so on. However, we need the energy. So basically, when it comes to energies, what we need is we enter the differences in energy. So we have, for instance, let's take this one. So here the first parameter is a scaling parameter, which is actually what we saw in the equation in the in the presentation, where we have the sigma parameters, and that's what is called. It's actually the tolerance parameter. So this actually shows the error in your DFT energies that is being reported. And then here we give the energy entry as a difference in the energies between the geometries. So here we have the first geometry, and then we use a division by 1 or 2 depending on if it's a monomer or a polymer, and so on. And one of the things that you should be very careful about this entering this energy entry is that it should be stoichiometrically written in such a way that it represents a chemical reaction. So that is the idea. So we have the first geometry divided by 1 minus the second geometry divided by 1 and gives the energy value, which is 0. So that is the format that is accepted by ReaxFF. Now it can also do it with the multiple type of entries, multiple geometries in a line, but there is a limit in the number of entries that you can have in one line. So probably you may have to do it in multiple lines. So without getting more into the details, I would like to, if you have more questions about these things, you can always contact me. Now I would like to go further into the core of this presentation, which is the ReaxFF of force field parameterization using this Monte Carlo algorithm. So what we have now is that basically we have the geofile. So geofile, which actually contains a set of geometries. So we have different geometries. So you can see that it has periodic as well as non-periodic geometries. Now there are a few things that you have to keep in mind when you generate this geofile. Is that for a particular geometry there is a keyword called description, and the description actually says that is the identity of that geometry. So here this geometry this molecule is being identified as OH separate, which that is a name of that geometry. Now this has to be unique. You cannot have multiple name for multiple. You cannot use the same keyword again and again in multiple geometries. So that can cause issues. Now that is one thing, and another thing is that by default ReaxFF assumes that whatever geometry that you have is for geometry minimization. Suppose you want to have single point calculations in your training set, then you can change the geometry optimization to single point by just using this keyword like this. So you write it like this: RU type and single point, and then this geometry will be taken as single point calculation. This is also reported in the ReaxFF manual. So if you have if you need more details, you can refer to that. Now that's all about the geofile, and then we have the training set file. As I've shown you, this contains the charge information, bond information, energy information, and so on. And that is our target. That is what we want to achieve. And then starting force field. This is a force field which is not optimized. So, but then it's working. So it's a typical force field. And then we have something called in our implementation. It's what we use is called we have bounds in the parameter optimization. So what we specify here is that with a max and min file, we specify that the parameters should not go beyond this particular bound. So this is a force field max file. So here you can see the maximum bound, the upper bound for all the parameters, for the force field. And one of the things is that you have to make sure that this parameter, the format of this file should be exactly identical to that of the force field, the starting force field. And then similarly, we have the min force field. Here also it shows the parameters which are which shows the lower bound for the parameters. And then what we have is another one is bool file, which actually says that this particular parameters, which all parameters have to be optimized. So here a value of 0 means no need to optimize, but a value of 1 means it has to be optimized. So here what I'm doing now is that I'm optimizing hydrogen and oxygen parameters. And of course, I wouldn't optimize some which are elementary properties such as atomic mass and valency and so on. So those kind of things we don't optimize, but we optimize all the other parameters. That's why we have some zeros here and some 1 here. And then I optimize the bond parameters, which is 2, 3. That's a OH bond. And so on. So and the off-diagonal parameters and so on. So I have set of parameters that needs to be optimized. So these are the things that you need to have in this folder. And once you have these folder, and you also must have in ReaxFF implementation for ADF, you need to have this file where it's just a one-liner. So I opt parameter with an integer value of 4. That has to be there. So once you have all these files, what you basically do is you type ADF bin and ReaxFF. I just type the log. I just dump all the information in the log file. So it started the run. Okay. Yeah, so here the optimization has started. So here you can track the optimization by tracking this file mc of ffoptimizer.log. So here you can see that the iteration number 0, this is the starting error that it had for the parameter. Then at each iteration, it makes new proposition for the parameters, for the selected number of parameters, and then depending on the probability, depending on the criteria that is mentioned, it either accepts or rejects the move. And here, what it shows here is a star is star means that particular move is accepted, and if there's no star, then that is not accepted. Now, I before getting let it run for the moment, I will just show you some other technique, other stuff which are involved in this calculation. So, which is one of the thing is the control file. I didn't say anything about the control file. So the control file parameters are the explanation for the parameters are shown in the website. Well, I would also like to share the meaning of these parameters. So during forceful optimization, the parameters which are above this parameters are irrelevant. They are not relevant for this calculation, but parameters are relevant. And here it shows the maximum number of iterations. Here I just gave 30 just to make sure that the calculation runs quite fast. And then here is the MCF of optimizer parameter, and then here is the initial beta parameter. That's the one that I mentioned to you. That's the beta parameter, beta value. Then the next thing is we increase or decrease the beta value by this particular value in this parameter. So the meaning of this parameter is that we increase or decrease the value. The explanation is given there. And then this is the scaling, the beta scaling, which is we divide the beta parameter by this particular particular number, and this is MC step. That's the difference between fossil max and fossil min divided by MCRXD, and MCRXDD is this one. So what it means is that for each parameter, this MMC program it calculates the range for each parameter, which is nothing but the difference between possible max and possible min, and then divide this range by this particular number. So we divide that into 500 steps. So that will be that will be the maximum range for each trial, each proposition. So that is the maximum probability that at each step a parameter can jump at once. So that's the idea. So if it can always be below that, which means that the random propositions are done with a probability from 0 to 1. So if it is 1, the maximum that it can get attained is specified by these settings. Now, this is something the maximum allowed maximum step size, which is that this. Okay, I'll explain a bit later then that one. This is MCS CPS. This is the parameter which actually scales this parameter space up or down depending on the acceptance rate. So here during this MCSF run, what we have is something called acceptance rate. We calculate the acceptance rate, and if the acceptance rate is higher, then the parameter space will be extended in the sense that the scope of the parameter space is increased by this this parameter. So we scale this parameter space by this parameter, and if the acceptance rate is lower, we scale down the parameter space by this particular value. So that is what is specified by this one. So when we do a typical simulated annealing procedure, if the temperature is high, then we will see that almost all the steps will be accepted. So in such a run, in order to maintain this acceptance rate, this program increases this parameter space by scaling this MC step value. So that is done automatically, and if the temperature is lower, then we have to reduce the parameter space, and that is also done by scaling down this parameter. So that is automatically taken care of by calculating acceptance rate on the go. So that's a good thing about this algorithm. So the whole idea is that based based on the acceptance, or in other words, it actually tries to maintain the acceptance rate by scaling this parameter space up or down. So that is the idea. Now, then here we have the target acceptance rate, and then here I explain this one, and this is the number of maximum of iterations. That's 2000. That's 56. Now, let's check how far we are with optimization. So we just we have said we are doing quite well here. So you can see that I'll show you how it's so I'll just open it here. So we started with an error of 9830, and you can see that within 10 minutes we have reached almost almost 748. We've got a reduction of around 25%. So you can see how much fast it's going down. The error is going down, and there are no much problems. So it's going well. Typically, from my experience, for this particular force field, we get an error reduction of almost 50%. That's I hope that will get, but I don't expect it to happen very soon. But I'm sure if you wait long enough, we should get it. Now, this is so. Let me say what is being printed out here. So, well, I forgot to say something in the console file. So that is um, there's something, which is that in this method we do not make proposition for all the parameters at the same time at each iteration. What it does is that it randomly picks a set of parameters and randomly picks, like in this case, what I specify here is that with this parameter, so go to explain this one. This is the fraction of variables active at each step. So which means that 10% of the parameters which are specified in the post-fill bool file are being changed at each iteration. So the selection is done randomly. So that is what I wanted to explain here. So once I have this one, yes. So here we have this. This is the iteration number, and this is the current error for each proposition. And then here it actually shows the the number of parameters which has changed at this particular iteration. So here it shows it's 11. So you can see that it's randomly changing. And then here it says this one is what's that? Let me check. So that's that's bounded value, which is actually means that one parameter during the change during the new proposition, one parameter has been bounded by the upper limit or lower limit, and this actually shows that the number of accepted moves so far, the number of rejected moves, and it shows the acceptance rate. And one thing to remember is that, as far as I understand, this acceptance rate is updated only once in 10 iterations. And then here it shows the beta parameter and then the maximum step that is shown. And here Alexei has implemented something called distance, which actually shows the distance from the starting force field to the current value in the high dimension parameter in the high dimension parameter space. So consider this set of parameters as a point in high dimension space, and this actually shows the distance from the origin, not the origin, but the starting force field. Now it shows the time. This is the time, so that makes it sad. So that is good. Now, I wanted to say something else. Yes. Now I will just show you a simulated annealing procedure. The way to do simulated annealing is uh, calculating just by doing some manipulation with the control file. So that's just go back to the control file. So in a simulated annealing procedure, you have to set the initial beta parameter, which should be approximately equal to point. Um, so the initial acceptance rate should be somewhere close to 0.2 or 0.5, depending on what you want. You have to specify what the acceptance rate that you want to set. So let's say if it's 0.5, then the probability of exponential minus or the Boltzmann factor should be equal to 0.5, which means that exponential beta multiplied by delta E should be equal to 0.5. So in this case, what we have here is that we have the E value, energy value. So we have around 9,800 or so, somewhere of that range, and multiplied by beta should be an exponential of. So instead of doing that, I would like to take the logarithm of 0.5. This. Yeah, so here comes the logarithm, and then based on the logarithm, you can calculate. So this should be the beta, so that should be minus, so beta should be um, mm, delta E divided by this value, which is around 9,400 divided by, sorry, this value divided by, divided by 9,800. So this should be your initial beta. So you set this as the initial beta, which is a pretty high temperature, which actually shows that at this temperature, the acceptance rate will be approximately 50%, and then you set the beta scaling parameter, which you can choose. I usually choose around 1 point. Sorry, this has to be less than 1. So I usually choose around 999, and then I also allow this parameter space, which needs to be scaled. Yes, that's the scale. So I choose this as it's around 1.1 or so, 1.01 or 1.1, depending on what you want. It's all about having some experience with the parameters. So the settings that I've shown may not exactly work for all the postings. So you just have to try and change these parameters to see which one really works for your system. But one thing is guaranteed that at the if you choose after a few trials, you will get a feel about it. And one thing is guaranteed that you will definitely find a minima. I mean, if you want to really find a global minima, then I would just go with uh, precisely with simulator and annealing. At the same time, I would also try different runs at the same time. I do 5-6 runs in parallel, and then check which one gets converged to the lowest point. And one of the things that we notice is that in most of the runs we can see that uh, if you run in parallel, almost all the runs will come closer to the to the lowest possible value at after a certain number of iterations. So after sufficiently long time. So in that way, we can say that if you run it multiple times, if you have multiple runs going on, then at least one of them will find a global minima for sure. So again, this is a random. This is a Monte Carlo method. Of course, you cannot have. Yeah, it's all randomly calculated. I mean, the parameters are the proportion randomly. So therefore, we cannot guarantee that within a certain number of iterations it should reach a local minima. But one thing is guaranteed that after sufficient enough of run, I mean sufficient, if you wait sufficiently long enough, you should get the global minima. So that is guaranteed in this procedure. Now let's have a look at what's happening with our. So far the error has been reduced to 72.4, so you can see that it's going pretty nicely. So within a short time, you can see that this is giving sufficiently, you know, it's the error is getting minimized very fast. So that much it's all about the minimization. So I would like to be happy to hear from you about some questions if you have. And thank you all for listening. And if you have further questions, you can always contact me by email, or you can also contact Fedor or Alexei and Hans, who's also working on this. So thank you very much. Oh, okay. So I have one question coming in. I'm not sure what what you want because you say it's no question for the moment. Well, I'll try to answer this in a short way. Does the program always take the last geometries during the post-field optimization or the initial one, or can you choose this option? Yeah. Okay. Yeah. So the question is saying, does it take the last geometry? Well, it always takes the initial geofile, if that is what you're asking. So it um, it um, it doesn't take the last geometry because we are not sure if the parameters proposed at each step are accurate, and therefore we do not trust them unless they are the global minimum or they are really good. So we do not want to count on that. So we do not take that and we always take the initial geofile for postal optimization. Well, can I choose this option? Yeah. Well. Mm, uh, yeah, I think that's something that. Well, I think yes. I think that is being implemented by Alexei already. So which is actually there is something called iStop file, which I did not explain it properly. So here, I'm not sure if Alexei has implemented it. No, I don't think he has implemented it. So far you cannot have this option. You cannot choose this option. But then again, to continue on that line, um, I have another code which actually does that thing for you. If you really want that immediately, you can always access that code and then you can try that out. So you can send me a mail post and I'll I'll help you with that if you really want to do that. Yes, yeah. So yeah. Yes, thanks a lot. Yeah. Yeah, thanks. We just stop the recording.